So when I teach students about the conservation of energy, I'd love to first get them to do the energy skate park simulation, because it just so wonderfully typifies everything that we're trying to communicate when we're trying to teach conservation of energy. When the skateboarder starts up on the high end of the ramp, he's got a lot of gravitational potential energy, right? Because remember that GPE is equal to mgh, right? Where h is the height. So if the height goes up, then he's got a lot of that gravitational potential energy. And he's just kind of sitting there, right? Not a lot of kinetic energy. But when he gets down to the bottom of the hill, he's got a lot of kinetic energy, because all that energy that he had stored by virtue of the fact that he was high up on the side of the skate park, when he got down to the bottom, he was going pretty fast. And that was 1/2 mv squared. That's our formula for kinetic energy. So he maxes out his speed when he's at the bottom of the ramp. But all that speed then can be used to carry him up to the other side of the skateboard park. And guess what? That if there was no losses in the system, if there was no friction between the wheels and the ground, all that kinetic energy would be turned back into the same amount of gravitational potential energy when he on this side. So if this is GPE1 and this is GPE2, conservation of energy says that GPE1 is going to equal to not only GPE2, but also the kinetic energy at the bottom of the ramp, right? So it's always conserved. But, you know, life is not perfect. Life is not always fair. We're going to lose some energy in this system because there is friction. So I want to introduce the concept now of mechanical energy. Mechanical energy isn't really a new type of energy. It is just the sum of all the energies in our mechanical system, which is the gravitational potential energy and the kinetic energy and the friction, which I'm going to write as TE, or for thermal energy, because friction causes heat. Let me give you an example. The skateboard park is a great example, but also everybody's been on a swing. So when you're on a swing, here's a swing, and say you don't put any energy into the system by swinging your feet, but you're in that back position, right? You're at that point where you're not moving anymore, and you're as high as you're going to get. So there is a certain, see if this is your down position over here, then there is a certain height associated with you being back that far, right? And so now all of your energy is in gravitational potential energy, right? And then when you swing and you're down at the bottom of your swing, then that's all the kinetic energy, right? But we have to account for the thermal energy, the losses in the system. Because if you don't swing your feet, eventually you're going to swing to a stop, because the energy is being taken out of your system. It's being dissipated through the heat in the joint up there at the top of the swing, right? So thermal energy is going to get lost. Gravitational potential energy, kinetic energy, thermal energy, that's all our mechanical energy. Let's say in this example that all of our energy is in gravitational potential energy. We're at the back of the swing. It's 1,000 joules. We're at the back of the swing, so there is no kinetic energy, and we haven't lost any energy in the system through heat. So the total mechanical energy in the system is 1,000 joules, right? So this is at the top of the swing. And then let's say at the bottom of the swing, if the law of conservation of energy says that you can't lose any energy in the system, so we have to maintain that thousand joules of energy. Doesn't matter whether we're at the top or the bottom. That energy we have to account for all that energy. Now we're at the bottom of the swing, so there's no gravitational potential energy, and we've converted gravitational potential energy to kinetic energy. But let's say that we find that if we measure our velocity at the bottom of the swing, we didn't quite come all the way back up to that 1,000 joules. Where did that energy go to? We don't have as much as energy as if we started. Well, if you measured the heat that was dissipated due to friction, that 10 joules was dissipated in the system. So this, I'm trying to give you an example with numbers, that if we start out with 1,000 joules of energy based on our height in the back of the swing, if it's not a perfect swing, if there's friction, maybe if that swing is squeaking a little bit, if you hear it squeak, you know you're losing energy somewhere. That's how we account for that. Okay?